This section will be all about the inverse of the matrix, and what we really mean is the multiplicative inverse of a matrix. So let's go back to, I don't know, middle school at some point when you're trying to solve 3x equals 1. Depending on your teacher, you may have talked about this differently. You might say 3 times x equals 1, and you wanted to undo, and the inverse operation of multiplication is division. Or you can think of multiplying by the multiplicative inverse to both sides. And then you get x equals 1/3. So just thinking about the idea of you're multiplying by the multiplicative inverse to undo that 3. So the same thing here when we have a matrix equation. So matrix A times the vector x equals a vector b. We cannot use division. There is no division in the matrix world. So we're going to be multiplying by an inverse. So we'll look at the details of that a little bit later. So here's the definition of the inverse of a matrix. Only square matrices have inverses, so we're starting off with a square matrix. If there exists another square matrix, we're going to call it C, so that when you multiply A times C or C times A, so both ways, that you get the identity matrix, then that matrix C is called your inverse. So in other words, if you multiply A and its inverse, you will get the identity. It does not always exist, but when it does exist, the inverse is denoted with this -1 power. So this is kind of like the function inverse notation. So if you use that notation, we have A times A inverse equals the identity. You also have A inverse times A equals the identity. More terminology, an invertible matrix is often referred to as non-singular. And if it is not invertible, then it is called singular. For a 2x2 matrix, there's a simple test to determine if A inverse exists. And Theorem 4 tells you that simple test, and that test right here. So if AD minus BC equals 0, then A is not invertible. And the reason it's not invertible is because that AD minus BC is a denominator, and you can't have 0 in the denominator. So we're going to use Theorem 4, which tells us how to find the inverse, to find the inverse of two matrices. So just to write out, like, what are our A, B, C, and D. So A would be 6, B is 3, C is 5, D is 4, basing that on what's in Theorem 4. And so A inverse is 1 over AD minus BC times the matrix D4, -3, -5, and 6. We get 1 over 9 times 4, -3, -5. We can bring a scalar inside, so we also could write this as 4/9, -3/9, -5/9, and 6/9. And you can also simplify those fractions that can be reduced. But either of those are fine for what the inverse is. So why don't you go ahead and look at the inverse for the next one. Hopefully, as you started to compute it, you saw that you got 40 over 40, which is a 1 over 0, so I don't even care what goes in here. This does not have an inverse, so I'm going to say it does not exist. So A inverse does not exist. When A inverse does exist, we use it to solve the matrix equation AX equals B. So starting with AX equals B, we can multiply on the left by A inverse. We know that A inverse times A is the identity, so we have the identity times X equals A inverse B. But identity times anything is going to give you that X back. So you have X equals A inverse times B. So this is another way we could find the X vector that we're looking for when we solve a matrix equation. Just to point out, we have solved this, and the way we have solved this is we augment A and B, and we row reduce, and that solves for x. So this is a second way to solve for x. So just in general, this is not the usual way you would solve for x for a variety of reasons. It can be very computationally intensive to find A inverse. Numerically, you can have a lot of errors when you find it. So there are lots of better computational techniques than using this A inverse B, but it's used a lot for theoretical computations. We are going to use it to solve this system of equations. So our A would be the coefficient matrix 6, 3, 5, 4, and B is the vector 1, -1. So I know that x is equal to A inverse times B. So I need to have A inverse. We have that A inverse is 1/9 times this 4, -3, -5, 6. Just to avoid fractions inside my matrix, I'm going to leave it like that. So we have that x equals this A inverse times B. B is 1, -1. Now multiplying, I'm going to leave my 1/9 out front for now. And I have 4 plus 3 is 7, -5 minus 6 is -11. So that is my solution. Again, I could write that as 7/9 and -11/9. Theorem 6 has some facts about invertible matrices. So if A is invertible, then the inverse of the inverse gets you back to A. So that's similar to transpose. If A and B are both invertible, then you can find the inverse of the product of two matrices, and notice the order swaps, just like with transpose. And then combining transpose and invertibility, this is saying it doesn't matter if you take the transpose first and then inverse, or if you do the inverse and then transpose it. Either way, it's the same. So we're going to prove the second one. And so the second one is saying that the inverse of AB is B inverse A inverse. So I'm going to say the definition of an inverse. There is a matrix C so that AB times C equals the identity, and C times AB equals the identity. So looking at AB times C equals the identity, by the associative property, I can rewrite that as A times BC equals the identity. Then I can apply A inverse on both sides. A inverse A times BC equals A inverse times the identity. The A inverse times A is the identity. On the right side, I have A inverse times I, so that's A inverse. And on the left side, identity times BC is just BC. Now if I multiply both sides on the left by B inverse, the B inverse B is the identity. And then I get C equals B inverse A inverse. So I see that C is B inverse times A inverse. And you can repeat that for this also. So just as a generalization from the theorem we just proved, if you had more than two matrices multiplied together and then try to invert it, it would reverse the order of all of them. So you'd have C inverse, B inverse, A inverse for the identity. We had a theorem that showed us how to compute the inverse of a 2x2, but what about larger matrices? In general, in order to find the inverse of a matrix, you augment it. So I'm looking at this. You augment it with the identity, and then you row reduce it until you get the identity on the left side. So you augment it with the identity on the right, and then you row reduce until you get the identity on the left. If you can't get the identity on the left, then it's not invertible. If it is row reducible to the identity on the left, then what's left over on the right is your inverse. So we're going to just apply this. So notice that A is a 3 by 3. I'm going to augment it with the 3 by 3 identity. And I'm going to row reduce. So the first thing I want to do is zero out below my 1. So I'm going to do row 2 is row 2 minus 4 row 1. At the same time, I'm going to say row 3 equals row 3 plus 2 row 1. So my first row is not changing. Second row is going to be 4 minus 4 is 0, negative 7 plus 8 is 1, 3 minus 4 is negative 1, 0 minus 4 is negative 4, 1 minus 0 is 1, 0 minus 0 is 0. For row 3 minus 2 row, plus 2 row 1, so negative 2 plus 2 is 0. 6 plus negative 4 is 2. Negative 4 plus 2 is negative 2. And 0 plus 2 is 2. 0 plus 0 is 0. 1 plus 0 is 1. I am now going to zero out this 2 by saying row 3 equals row 3 minus 2 row 2. So I have 0, 2 minus 2 is 0, negative 2 plus 2 is 0, 4 plus 8 is 12, not 4, 2 plus 8 is 10, 0 minus 2 is negative 2, 1, it's 1. Those last ones didn't really matter. At this point, I realize I cannot get the identity, which tells me A inverse does not exist. So again, just to repeat, once you get the identity on this side, whatever you're left with over here would be A inverse. If you can't get the identity on the left, then the inverse does not exist.